So the next speaker is Alonso Rodríguez from Universidade de Coruña in Spain. So he'll be talking about modular construction and optimization of the UZP Sparse format for SpMV on CPUs.
Someone's computer works with this. Presentation. Oh, yeah, that's not working. It seems like I got.
Yeah, it seems okay.
Thank you.
Okay, thank you too. Let me put the timer here. Okay, should work. It does. Can you hear me correctly? Okay, fantastic. So let's start. Hi, well, you already presented me. I'm Alonso Rodríguez from Universidade de Coruña from Spain. Today we are presenting this work, the modular construction and optimization for the UZP Sparse format for SpMV on CPUs. We are doing this in collaboration with the Colorado State University too. And let's get started because we will need some time here. So the main idea we had is to encode the non-zero coordinates using interoperable and affine lattices so that we can use regular loops for computations. Traditionally, what we did was store those sparse matrices in CSR or COO BCSR matrices, which basically we just store the data separately from the indices, which are stored in integer arrays. Our approach here is to encode these sparse coordinates directly with polyhedra, storing its structure, and thus using a generic but also tunable executor that only uses regular loops and so avoids any use of indirection arrays. This makes our new approach both modular, tunable, and kind of sim-dish depending on how we export it, and also general because, well, now we are going to work with matrices, but we can also extend that to tensors. So up there you have the traditional CSR SpMV loop, and on the X here, I don't know if you can see my cursor, you can see like here we do have that double indirection code, which makes it very difficult, if not impossible, to do gather-scatter operations, so we cannot vectorize it easily. And down there we have a simple specialized code for that matrix. In this case, a matrix could be a tensor. You have on the bottom left, so the red dots would be non-zeros. And so this specialized code is specific for this sparse matrix structure. Not that data, we could change the data, but not the structure, and it computes and accesses only those red dots. But what is a polyhedron, you may ask? So let's start with a matrix. A polyhedron is basically a region in space. In this case, we are dealing with integer polyhedrons, so this would be a two-dimensional polyhedron, and we can see this list of points as a square. This would be precisely the COO notation. It's not compressed. We can compress any of those dimensions, so we can also have this alternate description, which would be the polyhedral one. Here we have two inequalities here. And the polyhedron is described as the intersection of these two half-planes, expressed as such inequalities, and the points that lay inside that intersection are the points that are inside the polyhedron. So in this work, we will only model a polyhedra with integer points. And the question is, can we do more complex shapes? Yes, of course, we can. For example, if we want to tilt the vertical lines, this way we can do a diamond. We just need to add a little more restrictions to that shape of the polyhedron, and we can almost note any closed region of points in space. However, we do have a problem, which is what do we do with holes? If we want to represent this structure, for example, which would be very usual in some sparse matrices, depending on how we obtain them, we cannot do that. So that's when the C comes in. So we do intersect the image of this polyhedra with an affine integer lattice, and what we are doing basically here is having a 2x2 square, and we are just scaling it, adding a stride to the points it traverses. So that's the definition of a Z-polyhedron. So yeah, basically it can have holes. And also, and very important, this is a key message I want you to take home from this presentation, is that polyhedra, although it's a precisely defined mathematical concept, can be interpreted and viewed as different things. We have it like this: Z-polyhedra is a collection of points, but we can also define it as a sequence of traversal. Like, for example, we do have here 2 for loops that exactly map to the values in these inequalities and also to the values in the integer lattice. And so we will be dealing with this view of for loops equals polyhedra from now on. So this seems a little bit like the concept is simple, it's understandable. We are just mapping domains and iteration domains basically, but this is not easy at all. So basically, let's have this HB CAN 1072, which is a medium size matrix from SuiteSparse, and this can be represented with 870 polyhedra of up to 8 dimensions. But let's remember, 8 dimensions, unless we do loop fusion, but we are not going into that detail, should be represented with 8 consecutive, like nested for loops, which is sometimes not good. So what we are doing to do now, our approach is use more polyhedra, but of lower dimensionality, usually dimensionality 1 or 2 at most. In terms of speed, because well, we are in the HPC conference, so we do scale quite well. We can reconstruct matrices with 100 million non-zeros in a matter of minutes, and our time scales almost linearly in terms of non-zeros. So we do perform quite well in that regard, and our way of working will be just mine for simple patterns and then tune it later. I will show you. So Z-polyhedrons and polyhedra have been around for many years. These are like a very usual concept in mathematics, but they are not new for us at all. In our research groups, we have explored this firstly in here at PLDI'25 with the DSCG sparse matrix multiplication. What we did was basically take a sparse matrix and then create an ad hoc binary so that it performed all the necessary operations, all one by the next one. So it has some, like the only pro we found there is that we found a way to do that without using iteration arrays, but there are several cons. The first one is that the binary size is huge, so it's basically proportional to the size of the matrix. And then from that come some other problems, like we flood the instruction cache because we are dispatching a lot of instructions. And also we technically could auto-vectorize because it's just a sequence of FMAs. But if you have ever tried to compile 100 million lines of code with GCC, usually it's segfaults. So we just proved that that was a concept and that was feasible. Next, we iterated on it with Macbeth, which is the fastest we have found in the literature. And we implemented a two-stage scheduling approach. Firstly, we mined for the patterns, just as the previous paper, but then by modifying the compiler, we managed to emit AVX code, so we had a significant speed up over in some places, as you will see next. So in this work, what we are trying to do, and what we successfully do, is have the best of both worlds, have also the separated data from the executor that we have in CSR or other structures, while also leveraging the performance of Macbeth without the need of a specific binary for each sparse structure. So for that, we do have a 4-step plan. The first thing we need to do is define a UZP sparse format. UZP stands for Union of Z-polyhedra sparse format. This format encodes Z-polyhedra shapes in the dictionary, just the different ones, and then a list of origins, which are instances of those shapes, and we store like the beginning point of them. Then we developed a tool called Z-polyhedrator. There's no Z for some reason. It's a Rust-based tool that quickly mines for Z-polyhedra, for only a small Z-polyhedra, from a matrix market file, and then we use tuners, and tuners are key for this to work, because from these tuners, we will see later, we will make the performance go up. So given this, we'll have some generated executors, also maybe produced by tuners. In this case, yes, they are. And in our experiments, UZP outperforms on average all baseless tested for SpMV on CPUs, both single and multi-core, both cold and hot cache, except for Macbeth. Our workflow pipeline will be like this. We would take an input matrix, and we'll pipe it through, we would send it to Z-polyhedrator with a user-defined pattern file for it to mine for patterns. Then we would use a tuner, although it is not necessarily. We could just take the UZP file and send it directly to the generic executor. Or we can take the optimized UZP file, pipe it through an optimized generic executor, and perform any sparse operation we want to perform. In this case, we are just performing SpMV. This would be an example synthetic matrix we have created, and we have both the COO and CSR formats here. And to compare that, we have down there the UZP Sparse format. What we do is we find these polyhedrons, find these shapes. I will use these words interchangeably. And we find 3 different shapes with 4 instances of them. So the shape 1 would be the green one. We can see we have 2 instances of them. We also have shape 2 and shape 3, which will be red and the black one, although these are not that important. And also we have 2 dangling points. What do we do with them? So with these dangling points, what we do is encode them in the most optimal already existing representation. In this case, it's COO, but it could also be CSR depending on the layout of these points. But we are not limited to this. We have another thing which we can do is just represent these as length 1 polyhedrons, and this has a very interesting side effect because we do have pretty interesting compression ratios while also having constant time insertion, because what we need to do is basically just at an origin. If you do that repeatedly, the performance will drop, but it will still work. No need for recompression or re-exporting anything. We also can do here, and I will be a little bit fast here because we don't have that much time here. We do have these 2 instances of the same shape, so we can think of these. Remember the Z-polyhedra explanation? This is basically a 2x3 rectangle, just with a very big lattice between them. So we do encode this as 0, 1, 0, 0, 1 meaning from 0 to 1. So that will be the vertical dimension. Then we'll have from 0 to 2, that will be the horizontal dimension. And here we will encode the affine lattice. That will be 9, 0, 0 for the vertical stride and 0 to 0 for the horizontal ones, as well as the singular points, but we are not going into detail here. Here we have a mapping for SpMV code, but we are not going to detail either because these slides are for a 40-minute talk, and this is not. We do have not 40 minutes. So now that we have set the basics for the UZP Sparse format, we need to achieve some performance. And to achieve some performance, the tuners are key. We have implemented 3, but we do encourage any users that want to try this to implement their own tuners. And these tuners, what they do is, well, it says there's the explore alternate but equivalent representations of a sparse structure. Basically, the technical name is the explore equivalence classes, or they just change the way the points appear on the file. So firstly, we have the aggregation tuner. So let's assume we do have 2 shapes of the same characteristics, for example, 2 horizontal lines, and those 2 horizontal lines are contiguous to one another, so we can basically merge them. We do have 2 of length 8, we can merge them into of length 16. That is very important because that allows us to mine for patterns of reduced lengths, thus avoiding complexity explosion, and then merge them afterwards. Also, we do have the favor locality tuner, which reorders the way the origins appear in the file. So what this allows us is to have great cache performance, to have a lot of cache hits both in the input matrix as well as in the output vector. And also we implemented the specialized dictionary, which is the only tuner that doesn't modify the UZP file itself. What it does is, let's say we are working with a specific set of matrices. Usually, unless we're doing like random or very synthetic matrices, our matrices do have some kind of regularity. For example, if we are extracting the data of something that is symmetrical, we have symmetrical matrices, we may have the major row fully populated, we may have some bands here and there. So we usually have some similarities between those matrices, and we can use that to generate specialized tuners, which shouldn't be confused with tuners that only work on those matrices. They are still generic tuners, but they are tuned specially for our type of matrices, and the amount of speed that we obtain from that is pretty significant. So for our experimental setup, we choose we selected all of the 2,754 matrices from SuiteSparse, and we did a representative selection of them. So here we have plotted every single one SuiteSparse matrix, and with crosses, we have selected these are the selected ones. And as you may see, we have no particular bias towards any region. It's pretty representative of the whole spectrum. And also in the bottom left part, you can see a relation about the diagonality of the matrices. So we are not limited. So we basically do not do any kind of toy matrices or just diagonal matrices or any matrix that can be represented with a diagonal format. We do real-life matrices taken from SuiteSparse. And these are our results. So few notes here, because there's a lot to explain here. The first what we can look at the top right is that vanilla CSR is clearly bandwidth limited by the memory. And secondly, we can note here that our peak performance, although not the average, is very near the theoretical limit of the bandwidth itself. To put into perspective, the HPCG benchmark in this particular machine maxes out at 5.4 gigaflops, and we are achieving 9.21 with an average of 2.30. We also compete against CSR5 AVX2, which is a very popular algorithm out there in the literature, and also against PSC from Toronto, it's for partially straight codelet. And we basically max out this bandwidth speed. We also max out the bandwidth for this particular machine in one core double precision cold cache, which would mean just one iteration of the SpMV loop. But we do have some other more data. Here we also get better averages and peak performances against all of the other compared. In this case, we are doing 8 cores, double precision and hot cache, which would mean several iterations of the SpMV loop, and it doesn't necessarily mean better cache reutilization, but if programmed properly, we do have a lot more of cache hits, and thus improved performance. I want to say, I was supposed to say in the previous one, but I forgot. Every single point we have found we have plotted here, especially the BCSR one, because well, we can use block size between 2 and 32. We also can enable or disable tuning hints. All of these have been maxed out. So if basically for a single matrix, the best performance was achieved with tuning hints and 16 block size. That's the one that we have plotted. We are not cherry picking any data. And in general, we provide the best overall performance over every single other format, but a quick, very important disclaimer, although we are better in some cases, much better in some others, and the same in others, maybe worse, it's still important to note that if you are aiming for the top 1% performance, at the end of the day, what you need to do is still find the best suitable format for your specific case. It might be UZP. Our measurements show that for much more than half of the matrices it is, but for some others it is not. So you should be aiming for that if you're into that kind of performance maximization. So very quickly here, we are also comparing against ourselves, against Macbeth, which does have a very similar way of working, but with a very different philosophy. We do not outperform Macbeth on average, although we do have much higher peak performance, but it's just for a little amount of matrices. And also, we are not that strong against Macbeth in the median sizes. We are talking about 10 to the 3 to the 10 to the power of 4 non-zeros. Here, Macbeth is not also achieving higher average, but also the consistency is much better than UZP, which is all over the place. And finally, I want to show you here a little graph, which is not very easy to understand. So the green part is the uncompressible data. If we are doing lossless compression, this is the part that we cannot compress, which is the data itself, and the values of the non-zeros. Then in blue, we would have plotted the UZP metadata itself, the patterns and their strides. And in yellow, we have the dangling points, maybe data represented by CSR, COO, which is multiplied with its corresponding algorithm. And in red, starting from 1, would be the multiplier if we did not have this special region. So that's it. I hope you have found this talk interesting, and for a take-home message, we have successfully alleviated the limitations of our prior work using Z-polyhedra, and we are also distributing the UZP Sparse format and the associated complete toolchain to build, tune, and compute it. You can find that in our paper, and it's also up on GitHub. We encourage the users to program their own tuners if they need it for their own workflows, and that's it. I am very thankful for your attention. I'm more than happy to answer any questions or even offline. So thank you very much.
Any questions?
Kazan from McMaster, very interesting work.
Thank you.
One quick question is, how would this be extended if you apply data transformation? So you are finding a bunch of patterns and you model them as a polyhedral. So I believe like right now you just see it as a CSR, but what if you want to actually do the transformation? How would that change your approach?
Data transformation, you are speaking about modifying the sparse matrix itself, right?
Yes.
So we are basically, right now, we are targeting constant, well not constant, but constant structure matrices. I am not a physic, so I don't have the details, but I'm aware that it's useful for Hamiltonians and such things. Maybe conjugate gradient also benefits.
Oh yeah, for
largely.
sure. No, my point is like if you are allowed to restore the matrix.
Yeah, totally. But you would need either to re-export or retune the matrix if you want to have performance, but you can totally edit the matrix on the fly. So you can both add a non-zero by just appending it, or you can also remove a non-zero by either altering the polyhedron or just putting a zero there. It's still valid data. And also, yeah, that's basically it.
Have you seen any benefit of doing that? Like,
any benefit? Right now we have not tried doing that, I think, at least not me, because we are working with the Colorado State University too. We are trying right now the implementation in GPUs. We have some results, but I cannot assure anything, so we're still working on it. Also SpMV, we are still not strong on them, but because it depends on the way you tune and you export the code, we may have some results.
great, thanks.
Thank you.
All right, let's thank the speaker again.